Well, hello. My name is Daniel Morán. I am a developer in the core IoT and security chapters in FIWARE. And in this talk, we are going to complete the information my colleague Carlos gave you about the IoT chapter, the IoT components we offer in FIWARE. This is the outline of the talk we are going to give today. We are going to speak a bit about what the IoT agents are and what was the decisions that motivated their creations. We are going to speak a little bit about the interaction models the IoT agent implement between the devices and the context broker or NGSI components. We are going to speak about the provisioning APIs the IoT agent provides and why there is any need of provisioning of provision devices and registration of devices. And then we are going to give you a brief description of one of the practical examples, that is the lightweight machine-to-machine IoT agent we are currently developing. And in the last part, we are going to give you some hints and some tools in case you want to develop your own IoT agent to meet your custom needs. Well, first of all, what is the motivation between the creation of the IoT agents? Before the appearance of the IoT agents, the generic enabler FIWARE provided was the IDaaS. That was a monolithic application that offered a closed set of protocols that were deployed, that were designed to be executed as a service in the cloud, and you could also install the IDaaS as a single component in your machines. But it was meant to be more of a monolithic gateway, and we thought it lacked the flexibility developers will need in order to integrate their devices with the context broker. In order to fix that approximation, we split the functionality of the IDaaS into multiple IoT agents, and we designed some frameworks to let you create new IoT agents and create new IoT agents ourselves, but letting the user decide if the architecture of the IoT layer of their own applications, whether they want to use them as a service in the cloud or install their own IoT agents in their premises or in virtual machines in the labs and so on. The idea of the IoT agent is that an IoT agent is an NGSI bridge between a device protocol and the NGSI, that the context broker, that it's the language spoken by the context broker. But this translation between the device protocol and the NGSI protocol, it's not a free one-to-one translation, but it has a set of constraints. First of all, the IoT agents are based on one premise, that is that each device in the southbound of the IoT agent is represented by one entity, just one entity in the context broker, so that the conversion between the entity IDs of a particular service and device IDs in that service is a bidirectional one-to-one translation. The interactions between the device and the context broker are also constrained to three specific kinds of interactions that we are going to see in the next section. The IoT agents, apart from translating from the native device protocols to NGSI protocol, they provide some additional services. Well, before the additional services, the provisioning of devices. The IoT agents provide a provisioning API for the devices in order for the device owner to register the devices in the IoT agents. This step is important because some information about the device, like the API key, security information, trust tokens, as we are going to see later, or the service the device belongs to, has to be provisioned before the information of the device arrives to the IoT agent, so the IoT agent can provide all that information in the context operations it performs against the context broker. IoT agents also offer can offer additional services to the devices underneath them, like, for example, the security we have mentioned before and device registration, but also stats of the use of the IoT agent or the use of the devices and that kind of information. There are basically three kinds of interaction models between devices and the IoT agent. The main difference between the three interaction models is where the interaction begins, who begins the interaction, whether it is it's started by the device itself or it is started by the user, and also where the entity information or the information about the operation resides. The first interaction model, it's called the active attributes, and they are interactions that begins with an action that the device itself performs. That be the case, for example, of a device that goes to sleep, and from time to time it wakes up and sends a piece of data to the IoT agent. In this case, the interaction follows the flow you are seeing in the slide. The device sends a piece of data to the IoT agent. The IoT agent, in turn, sends that piece of data to the context broker, and the context broker stores that piece of data in its own database. Whenever a user query for information about active attributes, he is querying the information stored in the local database of the context broker. In the case of the lazy attributes, the flow runs the other way around. This case makes use of the context provider mechanisms that my colleague Fermin has just taught you. This requires that the use of lazy attributes requires that the IoT agent is registered as a context provider for the attributes, for the concrete lazy attributes of a specific device. This registration as the context provider occurs when you provision the device using the provisioning APIs, or in the case you provision groups of device that can be differentiated using the API key. It will take place whenever the device registers for the first time or send a piece of data for the first time to the IoT agent. The flow of the interaction is as follows. The interaction begins with the user making a context query or a context update to the context broker. The context broker reads the context provider register, detects that the IoT agent is a provider for the information the user is trying to access, and forwards the NGSI request, the same NGSI request the user performed, to the IoT agent. The IoT agent, in turn, transforms that request to the device protocol it's programmed to speak, and the device itself reads the information and returns it to the IoT agent, that will return it in turn until it reaches the user. The important thing that has to be highlighted in this model is that entity information does not reside locally in the context broker. All the entity information is always residing in the devices behind the IoT agent. So they can only be accessed via a direct query to the IoT agent. The last of the three interaction models is the commands. Well, one brief detail that the active attributes interaction model it's a write-only model. It's only used for the devices to write information in the context broker. But the lazy attributes model can be used both for querying information from the device and to write information into the device. For the case when we can execute commands over the device, the interaction model is quite similar to the interaction model for lazy attributes. The only difference is that when the IoT agent receives the forwarded query, it instantly returns the acknowledgement of that request and creates a new attribute in the device entity of the in the context broker in order to reflect the current state and the results, if any, of the execution of the command. This information is stored locally in the database of the context broker. Whenever the command finishes or raises an error or gives any kind of feedback, that feedback from the device is sent to the IoT agent and in turn it is the IoT agent updates that information and that status in the local database of the context broker. Yeah.
Do I have any way of knowing if the data has been propagated to the sensor or the command or whatever? Because if I write in the context broker something, I may have the illusion that
that's why we provide the two different interaction models, one for lazy writings and one for commands. Lazy writings are synchronous, so when the user sends a request to the context broker, the response to that request is not sent until the IoT agent has written the information in the device and has an answer to the written information. So in this case, you have a synchronous operation. So you have the information. You will have a context broker error if the information couldn't be written in the device. In the case of the commands, the process is asynchronous. I don't know. I have a sequence diagram here, but I'm afraid I will lose all my screens. So I will later I will show you a sequence diagram of how this works. But the idea is that the command, the redirection of the command from the context broker to the IoT agent is synchronous, but the request from the IoT agent to the device to execute the command is asynchronous. The IoT agent takes note. It has a queue, internal queue to process the command whenever it wants to process it, and then the information about the execution of the command will be stored in the special status and results attribute that you can find in the local instance of the context broker. The thing that the idea that the data resides in the context broker or in the context provider should be transparent to the user, really, because if you have if you do a query asking for the status that is local information and another lazy attribute that requires a forwarding, all these things should be resolved by the context broker and combined into one single entity that will be the response to the original user request. Okay. Any other question? Well, about the device provisioning models, as we have said before, in order for the IoT agent to process the request of the devices and to have all the information that it needs to write the context information into the context broker, it needs the devices to have some form of provisioning or auto-registration in the system. The IoT agents provides two ways of registering devices. First of all, there is the one on your right is the device per device pre-provision. Whenever a device owner wants its device to be used in the context broker, it can send a specific query for that particular device, indicating the device ID, the service that device belongs to, and all the information that they that the system needs to map the device information to the context broker, to the context element it's going to write in the context broker. This information includes also the types of attributes, whether one attribute in the southbound is active or is lazy or it's a command, and it may contains also for the protocols that need it. It may contains information to make the mapping between the identifiers of the southbound information to the attribute names in the context broker. The other way of provisioning devices is, instead of pre-provisioning one device at a time, device group information can be provisioned. In this device, if a device group information is provisioned, all the information about lazy attributes or about what kind of attributes are each one of the device attributes are, on the service information, trust tokens, API keys, and so. All of that information will be shared about all the among all the devices that connect through this device group. How the device group is defined, how the IoT agent determines to what device group device belongs, will be based in two pieces of data. That one of them called a resource, that it is somehow protocol dependent. It may be a port or a path or a specific URL the IoT agent offers just for devices in that device group, and an API key all those devices will share. Here we have a specific a payload for the device provision and API to show you what's the looks of that API. As you can see in the payload, there are basically the information can be divided in two types. The information about the device itself, the generic the information about the device, and the attribute information that indicates what is the kind of interaction each attribute is going to have with the context broker, and in also the type that attribute, the type that will be used to write that attribute in the context broker. The name of the device is the device ID. The entity name is the name that will be used for the entity that will represent the device in the context broker, and the entity type, the type of that entity. Just the name and the entity type are mandatory parameters that are completely needed to identify the device, and then to write the correct information in the context broker. In case the entity name is not present in the device provisioning request, the generic entity name based on the name and the entity type is generated for the device. The device provisioning API is a typical REST API. The first line you can see the path of the API, and it provides the typical typical operations: creation, retrieval, the removal, and modification. All of these operations has the same payload. The same thing you post to create a device ID will be the information you will get with a get on that device ID URL. The delete operation doesn't have any body, and in the modification operation you have to indicate the mandatory attributes, and all the attributes you put in the payload of a modification request will be changed in the internal representation of the device. Here, you have to notice also that the the multi-tenancy system that Fermin also spoke about in the previous talk is in use also for the IoT agents, and it's mandatory to use it. All the requests to the device provisioning API and the configuration, the device configuration API that we are going to see next, have to use the FIWARE service and FIWARE service path to indicate what service those devices belong to and what sub-service in the service you have used the device are going to be stored into. All this information will be stored along with the information you provide. There are more attributes than to the device provisioning request than those shown in the example in the right. But the only one that will be used in the exercises you are going to use is the internal attributes one. The internal attributes is a special attribute that will be dependent. Its semantics will be dependent on the IoT agent, and is meant to ease the task of translating the attribute information from the underlying device protocol to the NGSI protocol that will be used to create the entities belonging to the device. Yeah.
If I recall correctly, in the presentation made by Carlos, he registered the sensor types as well. So is this part of the new IoT agent architecture, or because you are basically doing something similar? I mean,
yeah. Yeah.
I'm sorry for the question. I'm a bit lost. I'm trying to recall the other presentation.
Yeah, I think it's pretty much the same. And in fact, the next API that we are talking about, the services API, I think it's very similar to the one used in the old SBC, EDAS, and so component.
So what was presented by Carlos was the old SBC.
Yeah, it was the old approach for the same problem, but the new approach is really an iteration over that approach. In fact, the EDAS component has been refactored to comply with all these guidelines and with these APIs. This API, the next version of the EDAS component that is going to be released, I think this month or on the month after, will have exactly this configuration and device provisioning APIs I'm going to present. I'm presenting just now.
So the idea is that any IoT agent should support this set of operations.
Yeah, that's the idea. All the IoT agents should behave from the northbound point of view. All should behave exactly the same, have the same type of interactions with the context broker, and the same configuration and device provisioning APIs. There are also some other APIs about statistics retrieving and so on, but all those APIs are still in development, so we are not going to present them. Okay. Well, any other question? Yeah.
But you have said before that IDAS was going to be replaced by IoT agents, or is going to be a new IDAS as long as new IoT agents?
And the new IDAS is a collection of IoT agents. Okay. The old code of IDAS have been refactored in order to comply with all this with this approach of the IoT gateway mechanisms.
So there will be no more IDAS. Yes, there will be just new IoT agents.
Yeah, I think the set that particular set of IoT agents will be released with the name IDAS, but they will really be just a collection of IoT agents.
And what about this IoT agent?
This everything that I have spoken about until now, it's generic for all the IoT agents.
Okay.
So the new version of IDAS will comply with these
Okay,
configuration APIs, will work with the type of attributes that I have, type of interactions I have described, and so on.
Okay, now it's clear. Thank you.
Okay. Any other question? Okay. The second device provisioning API provided by the IoT agents is the configuration API that gives you the ability or the feature of grouping multiple devices in order to give them the same, let them share API keys, trust, and this kind of information, and to get rid of the burden of having to pre-register every device you have to register that you want to connect in the system. By using the configuration API, you are going to as I told you before, you are going to define a resource and an API key that are protocol-specific information the IoT agent can use to detect whether a device belongs to one device, one configuration or device group, or another configuration. Once it has detected the device belongs to a particular configuration, it will use the information in that configuration to connect with the context broker. The mandatory resources in the configuration API are the resource and resource API key and type, and the device ID will be retrieved from the request made by the device itself. The configuration API, it's not exactly REST, and I will suggest you check the documentation about this, because the configuration API, as you can see, gives you the ability to define or to create multiple configurations in just one request. So this behavior, it's very similar to the one of the context elements in the context broker. This behavior also works for the modification and delete operations, but there are some caveats about how that works. So you better check the particular functioning. It won't be really needed for the exercises, apart from the how to make a post of a configuration API and use the configuration itself. And the last part of the generic IoT agent part of the talk are the security concerns. How all the information flows that we are using in the system, how they are implemented. Well, there are basically three kinds of interactions with the IoT agent. First of all, in the southbound, the interaction between the devices and the IoT agent is IoT agent specific. In the security in that interaction is IoT agent specific. In the case of you use co-op, you will have to use DTLS. If you use other protocol, you may use authentication, SSL. That's up to the particular IoT agent. So we are not going to explain this in these slides. There are two other flows that have to be secured. One of them is the access to the configuration APIs and device provision and API of the IoT agent. The access to that API, to those APIs, is secured with the standard FIWARE mechanism, that is the use of a PEP, of transparent PEP proxy on top of the IoT agent. And this leaves us with one interaction that has to be secured. That is how the IoT agent writes the information into the Orion context broker that will be in turn protected with a PEP proxy. The IoT agent being protected by a PEP proxy, the IoT agent needs a security token in order to access to write information in the context broker, the information coming from the device. the information, the security information in this case, will be retrieved by the use of trust tokens for the communication with the context broker. The trust tokens are a mechanism used in the Keystone identity manager that lets a user creates a permanent token for its identity and a particular role that lets the owner of that token create access tokens impersonating the user for that particular role. If you have any questions about this, have you understood what I? Well, more or less. The idea is that that a user can create a particular permanent token that will be associated with one of their device groups or one of their devices, and the IoT agent will use that device trust token to retrieve an access token. So the writings in the context broker will be made not with the permissions of the generic IoT agent component, but with the permissions of the user that had provisioned the device. The permissions of the user and the service that the user has used to provision that device. Okay. Any questions about this? Okay. So we can proceed. I would also like to, all of the information I have given you to this point is generic for all the IoT agents. But in order for you to practice this knowledge, we will give you give you some exercises that you can perform using one of the IoT agents that we are going to release this month. This particular IoT agent is the one for the OMA lightweight M2M protocol, and I'm going to give you a very brief information about what the lightweight M2M is, how it works, and the most common operations you are going to use or will be involved in the use of this protocol for the particular exercises we have prepared for the talk. Well, the lightweight M2M protocol is a protocol based on CoAP. CoAP is a protocol over UDP that tries to offer the same thing that REST APIs offer through HTTP, but over a mechanism over UDP using some confirmable message mechanisms, and using very small payloads based on binary transformations and binary options. So the communication overhead is as low as possible for that kind of constraint devices. CoAP offers the typical HTTP methods: the put, get, delete, and post. On top of that, lightweight M2M offers a protocol that is oriented to the use in IoT applications. And basically it offers two kinds of things. First of all, it offers an object model that can be used to describe the information on devices, on sensors, actuators, or constraint devices of that kind. This object model is a hierarchy-based model. It's based on three kinds of entities. First of all, the object types that will model a sensor or a particular kind of device. Instances of that particular object type, and resources that are attributes or pieces of data that that kind of objects can provide to their users. This resource hierarchy is transformed in the REST requests to a URL-like identifier, where the first identifier is the object type, the second one is the instance, and the third one the resource ID. The idea of the the lightweight M2M protocol is that all these IDs are not application specific or device specific, but a public ID registry is provided. That's called the OMA registry, where you can look for particular kinds of devices to know what the object ID of your device is, what the resource ID, what is the ID of the resource you are going to send, and so making the transformation between the semantics of the information and the description of the URL of that information automatic. The IoT agent uses this information with it has a local map to perform these transformations, so no more information should be needed when standard OMA registry objects are used to send information to the context broker. Apart from the object model, the lightweight M2M protocol offers several functionalities divided into 4 interfaces. The bootstrapping interface that defines how a device has to be connected to the system, and you don't have to worry about this in this particular example. It defines how to connect to bootstrap servers or read from local sources and so on. The client registration features define how a lightweight machine-to-machine client, that is a device, has to connect to the lightweight machine-to-machine server. The lightweight M2M protocol is a registration-oriented protocol, so every action performed by the client should be preceded by a registration. That you can't write information inside a lightweight machine-to-machine server without previously registering the device is going to make that right. And the client registration interface gives you the information about how that handshake between the client and the server has to be performed. And then the device management and information reporting interfaces offer the functionalities that let you manage the information in the lightweight machine-to-machine client. The device management offers information offers actions, or offers interaction types between the server and the client, where the server actively asks the client to perform the specific task or read or write a specific kinds of information using the URLs we defined earlier. And the information reporting defines a way for the server to request the client to make periodic or value-based updates on the values of some of the resources of the client. In this case, as you will see, the client itself cannot perform any kind of action initiated by itself to the server. The only way that the client can perform in that way is for the lightweight M2M server to ask first for the client to make such actions. This will be the reduced set of operations you will be using in the exercises. You really don't need to know the specific maps from these informations to the co-op request, or even how to perform the informations as a lightweight, the actions as a lightweight M2M server or client, because these actions, all the actions originated in the lightweight M2M server will be performed by the IoT agent without any need for you to interact with it. But I think it's fine to know what kind of actions it's this lightweight server is going to perform underneath the when you perform actions on the IoT agent. These are the five operations are the registration. The registration of the lightweight M2M client has to indicate 5 pieces of data. 2 of them are obviously the host and port of the server it's going to connect to. It also has to provide an endpoint name. The endpoint name is like the device ID, is an identifier that has to be unique for that client in that server. And a URL that can be used in the case of the device configurations to distinguish between different device configurations in the same server. The read and write operations will be used to map the query context and update context in lazy attributes, and the observe action is the one that will be used to map the active attributes of the client. Whenever a client reports, I forgot one important piece of information in the registration. When the client connects to the server, the client also indicates all the object types and instances the client supports for the server to know whether it can read a particular value, read a particular resource, or make any operation over those resources. The device management interface also provides some actions that can be used to discover information in the client, but I don't think we're going to use that in these practices. This was a brief description of the lightweight M2M protocol itself. Concerning the lightweight M2M IoT agent, this is the GitHub project of the agent. In the GitHub project, you will find some information about how to use the IoT agent and links to other information about IoT and IoT agents and the lightweight M2M protocol. This IoT agent, as all the IoT agents to this time, it's a work in progress. We are actively developing the IoT agents, so please be patient with if you find any bug. Just field it as an issue in GitHub, and we will try to solve it as soon as possible. The only thing you have to know about the IoT agent, the IoT agent should be all the IoT agents should be as transparent as possible to the user. The northbound interactions is always the same in all the IoT agents, and the southbound interaction should be the same as any other interaction with a server of that protocol. But there is a particular tweak you can use to customize the mappings from the device from the information in the southbound to the information in the northbound. As I told you before, there is an internal attributes you can add in the configuration API or the provisioning API that can be used to map specific types to a specific object ID or resource ID specifications. This is an example of that kind of mappings. These mappings have two motives or can be used in 2 different situations. One, when you want to map information that it's not in the OMA registry. OMA registry has a more or less wide offer of device types and device information, but it might be the case that you have a device that does not have an ID that is present in the OMA registry. In that case, you can define your own ID, your own custom ID, use it with the use of this mechanism. For the devices that already have a device ID in the OMA registry, the the AI attributes can be declared as active as active or command, declaring the attribute using the name in the name of the attribute in the device registry in the array of active array or lazy or commands array as the name of the attribute in the context broker. And in the case that any attributes are not declared in the provisioning API or configuration API payloads, all the attributes declared to be provided by the client in the registration will be mapped as lazy attributes in the IoT agent. So the IoT agent will register as context provider of all the attributes of the client. And just to finish, some hints about how to build an IoT agent. The idea we had in mind when we started developing the IoT agent mechanisms was to provide some frameworks to let you create the IoT, your specific IoT agents or IoT agents for different protocols that we do not support. And to this extent, we currently offer, or will offer this month, two frameworks. One to create IoT agents in Node.js, and the other one in C++. The orientation of those frameworks is a bit different, and I'll suggest you to read the documentation in order to know exactly what mechanisms you have to follow in order to create those IoT agents. In the specific case of Node.js, what we provide is a library that provides all the northbound features you should need in order to create an IoT agent. It provides the device configuration and the device provisioning and configuration APIs. It provides an NGSI client that can deal with features with information like with features like the multi-tenancy, security, and so on. And we provide a context provisioning server that will respond to the queries relayed by the context broker. So you only have to generate a handler for queries and a handler for updates, and link those actions on the context server, on the context provider server, to the appropriate actions in your southbound protocols. All southbound features are protocol specific, so we don't offer any kind of help there. So you will have to either rely on an external library or make an ad hoc development for that to implement that functionality. This is the case. If you search, if you look at the code of the lightweight machine-to-machine IoT agent, you will see that's the case. It's how we designed that IoT agent. The IoT agent is basically using two libraries. One northbound library that is our IoT agent framework for Node.js, and one southbound library that is a Node.js module to deal with lightweight machine-to-machine features. And that's, yeah.
I think some of us, we need to work with different languages.
Yeah.
And we need to develop our own agents.
Mm-hmm.
Is there any support from the FIWARE community that help us to work together?
We can give you support concerning the details of the IoT agent protocols. We can give you support on how to design the northbound of your libraries, but we are not sure we can give support in particular.
Sure,
language
I'm not
details.
asking about technical specific help. I'm more concerned about if I need to create a Java agent, and another guy here also needs the same. How can we find each other? Is there any specific forum for that?
Well, I don't know if that specific forum exists right now, so I will have to check with my colleagues.
Okay,
we are going to be in the labs, and
sure, yes.
maybe Leandro and Fermin knows.
I've been searching for FIWARE community, FIWARE forums, wherever, to try to find other developers.
We offer help in Stack Overflow, for example. So maybe just using the appropriate tag for FIWARE tag in Stack Overflow, you will end up having us at least looking at your problems.
Thank you.
Any other question?
The server you mentioned here is when I create the agent, the agent is a server per se. I mean, it's something is so. When you are mentioning the context provision server, is part of the library that
Yeah, it's part of the library. The library has some methods to start and stop the server, and it provides an endpoint, an HTTP endpoint with all the information of the
okay. Thank
provision APIs. Any other questions? Well, the last thing I will speak about is the exercises. We are going to link the exercise description in a presentation in SlideShare. And concerning the prerequisites of the exercises, all the exercises do need you to have the Node.js environment in your home, in your computer. It doesn't need not all of them, just the last one, I think, need you to have Node.js programming skills. But both the IoT agent and the lightweight machine-to-machine client we expect you to use are written in Node.js, so you will need to have the execution environment. We were providing a global IoT agent for you to test, but we have some problems, some network problems to use it, because the communication between the lightweight M2M client and the lightweight M2M server is a bidirectional communication, and without a public IP with no constraints on the firewalls, it's difficult for that to work. So I suggest you deploy your local IoT agent. There are instructions in the web page. We will be available also in the labs in order to help you. So I hope you won't find any trouble in doing that. And just the last thing, we are going to link this, to upload the presentation to SlideShare also, and you will find in the last page the resources with the address of the IoT agent framework, the lightweight M2M library we used to create the agent, and the agent itself, and some information about co-op and lightweight M2M. So if you don't have any questions, I think we are going to have the coffee break right now. Okay, thank you.